I'm seeing this kind of jointing, this pattern at right angles being eroded out, and that's kind of setting up the pattern for the lakes and the rivers. You can see that in this kind of aerial photo here, and you can just see where the fractures have been scoured out by the glaciers, and it's taken advantage of that broken up rock. And on ground level, it may not be quite as obvious, but it becomes apparent when you start looking at these channels and these areas where the rock has just got these little channels cut through it, long and straight. And even here, notice you can see the joining pattern running this way and this way. And notice that the channel doesn't necessarily follow directly along any one fracture, but it kind of zigzags its way through the fractures to kind of cut across diagonally. But it's taking advantage of that fracture pattern. So if you look at it, all of this part of the map, this is all fracture pattern, and I think you can kind of see how you can kind of hook together some of these long linear segments here, both at right angles, and that's developing the rock there. But if you go down into this part, you don't see that at all, because this dotted line here is basically the edge where the glacier was scouring everything off down to the bedrock, and where it just had so much debris to carry, it couldn't carry it all, and it started to dump it out, and all of this is covered with sands and gravels that the glacier left. So this is kind of the dividing line between erosion back here and deposition over here. Notice the river here. It's just kind of a meandering river. It's barely following any kind of basement fracture pattern control. The basement control is buried. A little of the basement control shows up, and you can see straight segments to the coastline, but you don't see much of the drainage. Whole different river pattern. One of the things that we see with these little fracture patterns is at the very end of them, it kind of just peters out, they stop, and the water goes into these fracture systems, fills the fracture, and it creates these wetland areas. These kind of dead-end areas. And these are extremely important areas for biodiversity. This is where all the snakes and the frogs and the beavers and the otters and the heron and all that stuff. This is where they love to hang out. And it's just an absolutely gorgeous area. All along the shorelines, you can pick these areas out. But they're very susceptible to changes in water. They're only 3, 4, 5 feet deep at the most. So when the water levels change, and they do fairly frequently, these areas really get hammered sometimes when they have a drop in water. In the fall of 2012, the water level was at the lowest it's ever been, ever recorded. And you can see it here in these two pictures. You can see where the water level had been the year before. It really kind of stands out. You can see the rocks really kind of were the ones along the shore. And if you look at the staining on the rocks, you can see that the water's been even higher than that. So you see these bathtub rings on the water around the whole area. And you can see the real significant changes in water level. So you can imagine what happens to these wetland areas on a pretty regular basis. So river systems really kind of shows you what a little bit of basement fracture control can do to set up the pattern. Okay, let's shift gears and talk about groundwater. I want to talk about the water now that's below the surface. In North America, we use 450 gazillion gallons of water every day. Okay. There's million, there's billion. All right, so we use a lot of water. And where do we get it? I mean, water, it's not that plentiful. How are we going to preserve it? How are we going to keep doing this? And if you look at groundwater, it's the water beneath the surface of the ground. So it's got to fill in those void spaces that are down there between the various rock grains. So rock type's probably going to be pretty significant, isn't it? I need rock and void space in it. So sedimentary rock should work real well. Rock like igneous rock, where all the grains are melted and fused into one another, not much void space. That's not going to work. And metamorphic rock, maybe, but probably not. So I'm limited to certain terrains. Rock type is also going to have a big control on the water quality. Swimming pools and spas all have filters. And one of the popular types of filters is simply a tank filled with sand. And as you run the water through that sand, the sand filters out the particulate matter and even can change the chemistry. And of course, you add chemicals to help that. So, in that case, you're really controlling the quality of the water. Now, if I have a limestone that is just fractured and the water is just running along this crack, there isn't going to be a whole lot of filtering going on there. You're going to be transmitting a lot of water, but not necessarily filtering. So limestone and sandstones are both good aquifers, or can be good aquifers, but they don't always produce the same quality of water, although they can produce the same kind of quantities of water. But groundwater is what we've come to rely on more and more and more. It used to be towns like Kalamazoo would pump their water out of the Kalamazoo River. They'd use a surface source. But as the area has populated, those surface sources have become more and more polluted and less usable for potable, clean water. So they have changed where they get their water from, and they've gotten them from subterranean aquifers that have natural filtering built into them. And of course, they filter and treat and all that stuff afterwards. But pollution has restricted our options a little bit. But right now, basically, it's estimated that about a third of the United States is underlain by aquifers of sufficient quality to be potable water. So how does this water get in there? Well, it basically soaks into the ground. It's a process called infiltration. And you see it every time it rains. You just kind of see the water disappear. And it's just moving down through the pores, through the cracks, and it's moving into the void spaces down between the various grains. And there are a number of things that are going to control how well infiltration works. Vegetation, for instance. If you can keep the water on the surface a little longer, it gives it more of a chance to infiltrate. If I have a grass surface, it's harder for the material, for the water to just run off. It kind of gets held in place by the grass. The grass also opens up cracks. It also helps the water move down through the system. Soil permeability. If I have a soil that's got a lot of clay in it, those fine-grained clays plug up the void space. And it makes it very difficult for the water to move through the soil. So clays become impermeable. They make it hard for water to get into it. Slope's another issue. I mean, again, it's that retention time, right? If I've got a flat area, the water can sit there and kind of take its time into it. But if I've got a steep slope, man, that water just runs right off, and it's gone. So slope can play a big role. Soil saturation. What if the soil's already saturated with water and all the void space is already filled with water? Where's the new rainfall going to go? It's not going to get into the soil, is it? It's going to be runoff. It's going to just have to find its way across the surface and find a way to get into a stream. And sometimes the amount and the rate at which the precipitation comes down really controls things. if I have a hard rainfall that just lasts for a little while, a lot of times that infiltration just can't happen fast enough. And basically the void space near the surface is plugged up with water trying to infiltrate, and the other stuff's still sitting on the surface waiting its turn. It's not going to just sit there. It's going to run off. What you want is one of those, nice 3-day slow soaking rains. It just comes down at a rate that the soil can accommodate, can take care of it. Makes a big difference as to how fast this water gets applied. So there are two things that we think about when we think about accommodating this water in the ground and moving it through the ground. The first is what we call porosity. And porosity is the void space between the actual physical grains of rock that make up the rock. Porosity is the void space, so this is where we store the water. But if the void space isn't connected, if there's no way to move fluid from one pore to another pore, how are you going to get the water in? And if it did slowly seep in there, how are you going to get it back out in any kind of a usable fashion? So that brings up the second term, the other thing that makes rock a good aquifer, and that is permeability. And permeability is simply a measure of how interconnected these pore spaces are. This way, it allows that fluid to move through the rock, to be transmitted to the well, to be withdrawn from the aquifer. If you can't get it out, it isn't going to do you much good, right? So porosity really talks about the volume of void space and the amount of water the rock can hold. The permeability really talks about the connectivity of these pore spaces and how well you can move the fluid through the rock. Both are critical. Let's kind of look at a couple different kinds of rock and a couple properties of rock like we've been talking about before. How about I have a basalt flow? Not going to have a lot of permeability and a lot of porosity, is it? I might have some gas vesicles near the top of the basalt flow, but they're maybe not connected very well. So I might have a lot of porosity in part of the rock, but very little permeability to make it usable. If I do have permeability connecting that porosity, it's going to be in a limited area because the gas making the vesicles is always bubbling out, and it's going to be right at the top of the unit, isn't it? And it's only if there was gas to escape from the magma. So not every basalt flow is going to have it. Certainly if I have granites, basement rock like that, I'm not going to have a whole lot. The only permeability and porosity I'm going to have there is if they're fractures. So just like we saw that river pattern developed by the fractures in the bedrock, well, there's probably a little groundwater associated with that too, but right along those fractures. Other than that, not much. How about in these sandstones? Now I've got some potential. Because the sandstones you can almost look at as a sponge. The pieces of rock making up the sponge framework, or the framework of the rock, and the void space being the holes in the sponge, being able to hold the water. And what we see is that the idea of sorting and rounding, which we talked about when we talked about sedimentary rocks, plays a big role in how much porosity and permeability I have in a sandstone. If it's poorly rounded, I've got less pore space because the little stuff can kind of fit into some of those pore spaces in between the bigger stuff, and it's going to cut down on the available porosity. Likewise, if it's poorly rounded, if it's well rounded, it means the only part of the particle that's going to touch next door is the part right at the point on one point on the curvature of that sphere. Whereas if it's very angular, again, it can kind of tuck into corners in between the other pieces and cut down across it. What if I have a nicely rounded, well-sorted rock, but it gets cemented up during the lithification process? That cement's only going to go in one place, isn't it? It's going to coat the grains and it's going to fill in the pore space. So immediately, it's cutting down on the permeability to get around between the spots, but it's really starting then to cut down on the porosity. So what if I have a rock with a lot of carbonate cement in it, and I start putting little acidic rainwater into the system, and instead of cementing it all together, I actually start dissolving some of the cements. Now I'm doing just the opposite of occluding or destroying porosity and permeability. Now I'm enhancing it, and we get what we call secondary porosity. It wasn't original to the deposition of the rock, but it happened later on during the diagenesis liquefaction process. So true or false? I'll let you guys work for a minute. Permeability is a measure of how well the porous space, the pores are interconnected. Permeability is critical. If you don't have that, you can't get much out of your porosity. So both things are going to be important. You can have all sorts of fluid down there, but if it's all tied up microscopically between grains or within molecular structures, and you can't get it out, all that fluid doesn't do any good. Okay, well, we kind of touched on this when we were talking about rivers, and that's the idea of the water table. And we said that the water table was basically exposed to the surface as the surface of a stream. Here, that was the water table. It was just that the surface of the land was lower than the water table, so the water table was on the surface. And you can think of kind of a number of different ways this might manifest itself. For instance, here I have a river. You can see the water surface in the river. There's my water table. And the water table is going to move from the bank area, and it's going to kind of be sub-parallel to the surface. So as the surface rises away from the river, the water table is going to rise along with it, not at the same rate. It's going to be a little lower. So right here, you see I can put in a well, and I'm going to hit the water table pretty fast. Up here, if I put in a well, then I'm going to have to dig a little deeper to get to that water table. And maybe there's a dip in the land, and all of a sudden, during a high period of the water table, that little dip now touches or goes a little below the water table, and now I've got a spring where water is leaking out onto the surface. Okay, it's August. The rains have pretty much gone away for a few weeks. The water table's going down, and I still have a little bit in the stream, but it's a lot lower. But look at my water table here. My well by the stream is okay. I dug it deep enough, so even though I hit water pretty fast, I knew in August the water table would be much lower, so I dug the well low enough to still intersect the water table. I have to lower the bucket down the well a little more, but I can still get it. No spring up here now. The water table's way below that, so the spring is gone. And look at the well I dug up here.